Okay, this is lesson 5.1 and 5.2 together. We're going to talk about natural logarithm, which is ln x. And we're going to talk about its differentiation, which means finding its derivative, and integration, which is finding its integral. So we're going to start with finding the derivative of ln. And there's two rules. The first one is if you take the derivative of ln x, you're going to get 1 over x. That's just the derivative pattern that works for ln. Now, that's if this is specifically an x. When you want the derivative of ln u, then u means that it could be x squared, or it could be x to the third plus 5, or it could be cosine, or it could be the square root of x. It could be a lot of different things. So u is the term for any other function rather than just a simple x. In that case, you're going to have 1 over u times du, which you could also rewrite that as du divided by u, which means it's the derivative of whatever this argument is divided by the function. So the derivative divided by the function makes the derivative of ln. So let's look at some examples. Some pretty simple ones first. We're going to look at the derivative of ln 2x. So following my pattern, I do 1 over 2x times the derivative of 2x, which is 2. And in this case, this one simplifies. I cancel the 2's and I get 1 over x for my derivative. For the next example, I'm going to do 1 over x squared plus 1 times the derivative of x squared plus 1, which is 2x. But I can put these together and write it as 2x over x squared plus 1, which fits the pattern that I talked about on the previous page of the derivative over the function. Okay, so let's look at some more practice. If we have a product like this one, where we have x times ln x, we can use the product rule, because remember we're talking about differentiation. We're talking about taking the derivative, so we have u dv plus v du. So I'm going to take x times the derivative of ln x, which would be 1 over x, plus ln x times the derivative of x, which would be 1. So simplify this and you have 1 plus ln x is the derivative of x ln x. Okay? Sometimes you can rewrite these problems. So I'm going to start out by writing this as f of x equals ln of x plus 1 to the 1/2 power. So I'm just changing the square root. Now, one of the things you might recall from logarithms is that if you have a power here, the power can be brought to the front. So I'm going to rewrite this as 1/2 ln x plus 1, which actually makes this a little bit simpler problem. So now if I want to take the derivative, f prime of x, 1/2 is just a coefficient, so we leave it there, and the derivative of ln x plus 1 is 1 over x plus 1 times the derivative of x plus 1, which would just be 1. So in the end, I'm left with 1 over 2x plus 2 for the derivative of ln of the square root of x plus 1. Rewriting it makes all the difference with logarithms. If you can rewrite it, you should. Alright, so let's look at this one. Remember when you did that expanding and combining of logarithms? You did it in Algebra 2 and in Pre-Cal, and you probably thought, I don't understand what the point of this is. Well, here's a really good point for this. When you have natural log, if you have things that are multiplied within the natural log, like these two things, they can be split up by addition. And when you divide by something inside the logarithm, then it can be split up into subtraction. And then we can go a step further, and I can say this is ln x, and this exponent here can be moved to the front because it's one of the rules of logarithms. So this would be 2 ln x squared plus 1. And then if I rewrite this square root right here, I rewrite this little grouping to the 1/2 power, then that 1/2 power also gets moved to the front. 2x cubed minus 1. Okay, so if you have multiplication inside of your natural logarithm, it becomes addition. And if you have division inside your natural logarithm, it becomes subtraction. Now that's as far as this will go, but let's now look at the derivative for this. ln x becomes 1 over x. The 2 is a coefficient, so it stays. The derivative of ln x squared plus 1 is 1 over x squared plus 1 times the derivative of x squared plus 1, which is 2x, minus 1/2, which is a coefficient. The derivative of ln 2x cubed minus 1 is going to be 1 over 2x cubed minus 1 times the derivative of 2x cubed minus 1, which is 6x squared. So I'm going to go through and I'm going to simplify this a little bit. So I've got 1 over x plus this 2 and this 2x can combine to be 4x over x squared plus 1 minus, on this side the 2 cancels with the 6 and makes that 3. So we have 3 in the numerator over 2x cubed minus 1 in the denominator, and there is my derivative. Now you might not have thought about this, but if we didn't do all of this rewriting, then in the original problem we would have a product rule and a quotient rule, on top of the fact that this is a square root, which would have made it a chain rule. So imagine doing a quotient rule with a product rule and a chain rule all in it versus rewriting it and making it a much simpler problem. Okay, so one of the things you're going to see is with some trigonometry, you may have to do a little rewriting. So if I want to take this derivative, actually the derivative part is pretty easy. If I want to take this derivative, keep in mind that the absolute value bars are just there because natural log, you cannot take the natural log of anything negative. So if you see absolute value bars, don't let that scare you. It's still going to be 1 divided by cosine x for the derivative times the derivative of cosine, which is negative sine x. So look what happens if I put this all together. That's going to be negative sine x over cosine x, which simplifies to become negative tangent x. So the derivative of natural log of absolute value cosine x happens to be negative tan x. Okay, that was the differentiation. Now let's look at some integration, and hopefully this will make a little bit of sense. If the derivative of ln x was 1 over x, then integrating 1 over x will take us back to ln x. And now here we see the absolute value bars come into play again, because remember, natural log, you cannot take a natural log of anything that's negative. So if we integrate 1 over x dx, we get natural log. If we integrate 1 over u du, we get natural log absolute value of u. Don't forget your plus c's. But the way to see this a little bit easier is to remember that 1 over x dx is the same thing as saying dx over x. So if you see a derivative divided by the original function, when you integrate it, it's going to become natural log of the denominator. So if this was integrating du over u, it integrates to become natural log of the denominator. And keep this in absolute value bars and plus c. So let's look at this. First of all, for this problem, I would start out by rewriting it because the 2 is a coefficient, we pull that out. That leaves me with 1 over x dx, and we just saw that 1 over x integrates to become natural log absolute value of the denominator, which in our case is x, plus c. So there's our answer, just like that. Alright, this one might be a little bit different, so let's see if we can't figure this out. Remember how with substitution we talked about is it complete? Well, I'm going to rewrite this as dx over 4x minus 1. All I'm doing is bringing these two terms, multiplying them together. Okay, now the derivative needs to be the top part and the original function needs to be the bottom. So if my bottom function is 4x minus 1, what is the derivative of 4x minus 1? Well, it's supposed to be 4 dx. And to balance that 4 that we just put in, we're going to put a 1/4 on the outside. So now when I integrate it, this takes the format of derivative divided by original function, which means it becomes the natural log of the denominator in absolute value bars plus c. That's all you got to do. Alright, so checking this next one to see if it's complete. If x squared plus 1 is my original function, is x its derivative? Well, it's almost its derivative. The derivative of x squared plus 1 would be 2x. So I put 1/2 on the outside to balance that. Now that it takes the format of the derivative over the original function, we have the 1/2 on the outside. This integrates to become ln of absolute value of x squared plus 1. This time I don't need the plus c because I have limits of integration from 0 to 3. So I can actually go ahead and solve this and be 1/2 ln of 3 squared plus 1 minus 1/2 ln of 0 squared plus 1. And as long as the term inside here is positive, we don't have to do anything with the absolute value bars. So this gives me 1/2 ln 10 minus 1/2 ln 1. Now, one of the things you may or may not remember is the natural log of 1 equals 0. So this is 1/2 ln 10 minus 0 times all this is just going to be 0. So that second part totally disappears. Okay, let's check this one. Is the numerator going to be the derivative of the bottom? Well, let's see. If I let the denominator be u, which sometimes we do, then the derivative of that would be 3x squared plus 1 dx. Well, look at that. So this is the du. I can actually replace it and put it as du if I want to. And x cubed plus x is u. And remember the dx actually went with this part here. So there's my problem. Du over u integrates to become ln absolute value u plus c. We know that u is actually x squared plus x, so this is ln of the absolute value of x cubed plus x. I said that wrong a second ago. I meant x cubed plus x plus c. And there you go. Alright, so what about this one? What would the derivative of x squared plus 2x be? This derivative would be 2x plus 2. Well, is this the derivative of the denominator? No, but it's pretty close. What if we put parentheses around this and put a 2 on the outside? Isn't that the same thing as 2x plus 2? So if I put a 2 on the inside, I have to put 1/2 on the outside. Now this is the derivative over the original function, which means it's natural log of the denominator in absolute value bars plus c. That's it. Okay, so now we want to integrate tangent. We've talked about integrating sine and integrating cosine, and if you know, like, something is the derivative of something, for example, secant squared is the derivative of tangent, so we can integrate secant squared because it just goes back to being tangent. But we don't actually have an integral of tangent because it's not the specific derivative of anything. So what we're going to do is we're going to rewrite this problem as sine x over cosine x. And it looks like I forgot my dx over here. Okay, so now that it's in fraction form, anytime you have a fraction, this is when you're going to start to think to yourself, is my numerator the derivative of my denominator? Is sine x the derivative of cosine x? It's almost the derivative of cosine x. If we put a little negative in there and balance it with a negative on the outside, then now all of a sudden this is the derivative over the original function, and that means it becomes ln of the denominator plus c. So, this is something you can actually memorize. What is the integration of tangent x? It's negative ln cosine x. Okay, so now I have all of these things for you. We know the integration of sine is negative cosine. We know the integration of cosine is positive sine. Oh, look at that, I forgot a plus c. We now know that the integration of tangent is negative natural log cosine u plus c. This is something you can memorize. You don't have to memorize it because you can work it out, but it is something that's useful to memorize. If you integrate cotangent u, you get the natural log of sine u. Whereas when you integrate tangent u, you get the natural log of cosine u, and it's negative. Now the two that probably aren't going to make much sense that you might want to just memorize are secant and cosecant. Secant becomes natural log of secant plus tangent, and cosecant becomes the negative natural log of cosecant plus cotangent. But these are things that you can put on a list to memorize, or you can pick the ones that make perfect sense to you, maybe like these ones, and keep them close to you, and then practice memorizing the ones that are maybe not quite so easy. Okay, so how could this work, putting some stuff all together? First of all, I'm always going to look at trig and see if I see an identity. And 1 plus tangent squared does equal secant squared. Okay, so I'm rewriting this. Now, that's the square root of secant squared. So the square root and the square cancel, so we're left with just secant from 0 to pi over 4. Now, I want to integrate this. What was that integration for secant? It was natural log, absolute value, secant x plus tangent x. And we have integration limits from 0 to pi over 4. So I'm going to have natural log of secant pi over 4 plus tangent pi over 4 minus natural log of secant 0 plus tangent 0. Alright, what is secant of pi over 4? Well, it's the reciprocal of cosine at pi over 4, so that's going to be 2 over the square root of 2. Tangent pi over 4 is 1. Secant at 0 is going to be the reciprocal of cosine at 0, which is 1, and tangent of 0 is 0. So now what I have is natural log, let me write it up here, natural log of 2 over the square root of 2, and that's a positive number, so I don't have to worry about whether or not I have absolute value bars. So it's 2 over the square root of 2 plus 1 minus the natural log of 1 plus 0, which is 1. And you might remember just a couple minutes ago I told you natural log of 1 is actually 0. So ln square root of 2 over the square root of 2 plus 1 is my solution. Okay, so I am actually going to have a worksheet for you to do some practice problems, because I have a worksheet that combines the derivatives and the integrals together, and we're going to work on natural log in class.